Okay, so we'll go ahead and get started. Today is March the 21st. It's our 20th class. Actually, 20 is quite close to 21. And what's special about our 21st class? It's halfway through. There are 42 Monday, Wednesday, Friday meetings. This coming Friday is the exact halfway point for us. Today we talk about a little more about tangent and then the other three trig functions. We haven't defined them yet, but we will. And then the next three classes, you can see, it's the only topic that we give 3 full classes to, inverse trig, whatever that means. We do have project number 6. Are we working on project 6? That's due on Friday. Project 6 is the one about the bicycle wheel. And then our next quiz is coming up on Monday. Any questions on the calendar? Okay, just some quick announcements, not about pre-calc. We had mentioned next Thursday, not tomorrow, but next Thursday is advising day. There are no day classes on advising day. I'm fairly certain I told you that night classes were on as scheduled on next Thursday night. I was wrong. Next Thursday night, there are no classes of any kind, okay? So next Thursday is just advising day. Classes are canceled, so you have a chance to meet with your academic advisor if you can get yourself in here. I didn't talk about the resume thing on advising day, did I? Okay, so there's a whole slew of activities planned for advising day besides just meeting with your advisor. But if you want to polish up an existing resume or just create one from scratch, you can meet with Kathy, who works here in the business department. And she's going to meet with folks from 9 to 10 on Thursday of next week over in the business studio in the East Building and help you make your resume powerful and effective and lots of good stuff. And there's a whole slew of other things happening that day, all kind of about advising and course selection and career building and things like that. So, you know, if you're able to get on campus on that day, take advantage of the stuff that is being offered. There's a lot of it. I think that an email was sent out to all students either this morning or last night just about the schedule of stuff happening on advising day. Can anybody confirm or deny that? So it should have come from Shane Hammond, I'm guessing, and it's just when did it come in yesterday? Or? It was there at 8 a.m. Okay. So go to your GCC student email. You will see a list of things, including this resume workshop, and you know, take advantage of the stuff happening that day if you're able to. Okay, so that's that. The other not pre-calc thing I wanted to mention, we had some students take part in the in this nationwide math competition exam thing. It happened right before break, and I just wanted to acknowledge that there are a couple of people in this room who were in our top 5. So GCC's team score is the sum of our top 5 individual scores, and so can I get Kyle to come on up and receive a certificate of merit for participating and being in our top 5. Congratulations. All right. Well done. And Allie, if you could come on up. And Allie is also in our top 5. Congratulations. And so I'll just post the scores are not all submitted yet, but here in the Northeast, you can see we are currently 8th. There are 20 schools that will submit their scores in the Northeast that participated. And so Allie and Kyle's scores are part of this 54.5 points that we earned. So well done, and thank you guys for participating. Okay, so on page 32, we'll dive into more trig stuff. And we start here with number 1, advance. Good. Kyle, number 2. Okay, and actually I think I should have written one more thing in that sentence. What's special about this particular picture that makes that sentence true? It's the unit circle, right? If that's a 1, then here's our definition. If it's not 1, the definitions change a little bit. We'll see them on the next page. I'll go back to Richard for 3. Okay, so looking at the picture, we know that the SOHCAHTOA thing should still apply. The tangent was opposite over adjacent. Which of these is the opposite side? That's the y. and which is the adjacent side, is the x. Does it matter whether or not you're in a unit circle? Nope, because this one doesn't grab the hypotenuse of the triangle. So the definition of tangent is y over x. We have now defined tangent not just for acute angles, really small angles, but any angle you can name. If you just go to a point on the circle, unit circle say, and you grab the y-coordinate and you divide by the x-coordinate, that's the tangent of the angle. Let's try number 4, 8. Okay, so I'm going to grab the unit circle from the first page. You guys can grab the unit circle from any page. But we're looking for 3 pi over 4. In which quadrant will we find 3 pi over 4? Okay, so 3 pi over 4 is here in the second quadrant. And I can see that there's my y-coordinate and there's my x-coordinate. And the definition of tangent is simply y divided by x. So the y is root 2 over 2 divided by the x, which is negative root 2 over 2. What does that equal to? Negative 1. The tangent of 3 pi over 4 is negative 1. That's one of the few angles that has a nice value for the tangent. Usually the tangent is some irrational number, but there it's tangent, the tangent is negative 1. So again, tangent is y over x. That's like the most important thing to know about the tangent function. Questions on that? Okay, so let's come back to page 32. It's here. And we'll go to, we'll just put the answer here. This one is equal to negative 1. All right, and we'll go to Tacitae for 5. All right, so it's the same picture. It's that angle theta, and I'm looking at the line that I'll highlight here in red. It continues. We've just drawn a little part of it here. What's the definition of slope in English? No formulas. Rise over run. How much is the rise? Yeah, looking at that point and that point, which are the only 2 points we have. The rise between those two things is the vertical part. It's the y. And how much is the run? It's the x. So the slope is rise over run, y over x. So the slope, rise over run, y over x. And where have we seen y over x today? It's the tangent of the angle. So if you happen to know the tangent of some angle, well, then you know the slope of that line. It's the same number. Does that agree with our 3 pi over 4 business? You guys remember 3 pi over 4 was this angle in the second quadrant? And 3 pi over 4 is the angle that's exactly halfway in the second quadrant. What's the slope of that line? Negative 1. Same as the tangent of 3 pi over 4. Okay, we'll go to 6. Emily? Okay, so let's jump ahead for just a moment to number 9. We'll come back. But I think 9 belongs here, so let's try it. Sam? Okay, so look at the picture. Don't even have to worry about the 20 degrees, just count boxes. Estimate the slope of that line. So rise over run, anybody have an estimate, maybe as a decimal? Roughly 1 over 3? You guys buy that? Like, I mean, it definitely goes through the origin there, and it almost hits the point at 3, 1, right? So it's close to 1 over 3. Is a little more or a little less, like which? Yeah, because the rise is a little bit bigger than 1. So maybe it's not really 1, maybe it's like 1.2 or something like that, roughly. 1/3 is about 0.3. So this would be something a little more than 0.3 repeating. Okay, so we'll say this is, maybe 0.35. I don't know what it is. Something a little more than 1/3. Okay, how would I find like a better estimate of what that slope is? Well, according to what we've seen, what is the slope of that line? Yeah, the slope is exactly tangent of 20. That's what the tangent is. It's always the slope of the line going through the origin there. So I can type in tangent of 20 on my calculator. It is. It's really easy to make a mistake if you don't know what you're looking for. If you hit sine, cosine, or tangent, before you hit the enter button, make sure you're in the right mode. In this semester, we were always going back and forth. This one happens to be degrees. It's very disconcerting to see those two things where a tangent of 20 is 2.3 or 2.2, but then in the next line, tangent of 20 is 0.36. You guys know that the 20s don't mean the same thing. 0.36, is that reasonable from our guess? Quite reasonable, okay? So if you want to know the slope of a line and you know the angle, tangent of that angle, that's the slope. What was it, 0.36 something? 64, okay. All right, let's come back to the one that we had skipped. At the bottom, we're on number 7. Undo. And we'll go to Todd. Okay, sine of theta. What letter was sine of theta, x or y? Sine of theta is y. What is cosine of theta? It is x. If you see y over x, you're now thinking a couple of things. What is y over x? It's the tangent of the angle. So our conclusion is that the tangent of theta is really the same as the sine of theta divided by cosine of theta. I know, I just got too eager to wear my tangent shirt. It would have been better today. What did it say on the front? It said sine over cosine. On the back, best way to get a tan. Yeah, I got excited to wear my shirt. Okay, so tangent is sine over cosine, and just a real quick kind of confirmation of that on the calculator. If I were to type in, for example, sine of 20 and divide it by cosine of 20, can you guys tell me what we're going to get? Are we going to get exactly the 0.36? Okay, tangent of 20 is the same as sine of 20 over cosine of 20. Great. Okay, we'll go to the next page and Topher. Okay, so lots of different ways to think about the tangent function. It means all of these things at the same time. Kelsey, number 10. Okay, so let's give this a shot. So I'm going to draw my axes here, and we're going to put our 90-degree angle out there, and negative 90 here. And the goal is to graph this y equals tangent of theta. We've already seen y equals sine of theta. And you guys with your finger in the air, what does y equals sine of theta look like? And so we've seen this kind of up and down, repeating type thing. And cosine looks almost identical. Let's figure out what tangent looks like. So we're going to think about the unit circle. I'm actually not going to go all the way back to the beginning. I'm just going to use this picture right here. So suppose that we start our journey here with an angle that's 0 degrees. So that starting angle right there. The coordinates here are what? 1, 0. And the tangent is y divided by x. How much is y divided by x here? 0 divided by 1 is just 0. So the tangent of 0 degrees is 0. Super. We just found our first point. Where is it? It's at 0 degrees, and 0 is the answer. So the tangent graph hits the origin. Let's pick a new point. Suppose that we go to a point that's up here. I'm going to go to like this. I went the wrong way. I'm going to go to the 45-degree angle, which is close enough to the one that's drawn here. If you're at 45 degrees, the y divided by the x, well, what's it going to be? It's going to be 1. They won't both be 1, but it's going to be the same number. If you're perfectly going through this first quadrant here, the slope of that line is 1. The y and the x will be exactly the same. It happens they're both root 2 over 2. We saw them earlier. So the tangent of 45 degrees is how much? Is 1. Tangent of 45 degrees is 1. Okay, so I go to 45 degrees. There, I'll say that this is the number 1, and that's another point that's on the tangent graph. Can you guys look at the picture of the circle again and think about what the slope of what tangent of negative 45 degrees is? We see it's negative 1. Okay. So that's another point, a third point we can graph or plot for the tangent graph. So negative 45, it's down here at negative 1. Okay, and I've got 3 points. And at the moment, perhaps it does the same kind of thing that sine and cosine do. Maybe it's like it comes down and goes up and comes down, like something like that. We've got 3 points that it might still kind of do this curvy up and down type thing. Okay, let's find another point. How about we go to 46 degrees? 46 degrees. I don't want to use the calculator just yet, but we will in a second. But if I go to 46 degrees, what happens to the slope of that line? Increases. If it's a 45-degree angle and then you go to 46, it increases. Not by a whole lot, but it gets a tiny bit steeper. So what happens to the tangent at 46 degrees? It increases. Tangent of 45 was 1. Tangent of 46, 1.04. I don't know. It's a little bigger than 1. Okay, this means that it does not do what I had said maybe it does, because 1 is no longer the cap. It's no longer the maximum. Okay, so let's see if we can get to where Garrett is. If I go to 46 degrees, I'm saying the tangent has gotten a tiny bit bigger. That's an exaggeration. If you type in tangent 46, can somebody tell us a better estimate? 1.01. Okay, so it hasn't increased by much, but it's a little bigger than 1. And now let's kind of keep playing this game. If you keep increasing the angle, what happens to the slope? It gets bigger and bigger and bigger. And what if you're at like 89 degrees? Which basically, like if I asked you to draw an 89-degree angle, you would pretty much draw the y-axis. I mean, like it's so close to being straight up. And the slope of an 89-degree angle is really, really big. So what's the biggest slope you could get here? There really isn't one. Do you guys agree? We could get this line to be as vertical as we want, just shy of being perpendicular here. So where do we get up to infinity? What angle is the one where the slope is infinity? Is a 90-degree angle. If you make your way to 90 degrees, the tangent gets bigger and bigger and bigger. And we'll just kind of confirm real quick on the calculator. If I were to find the tangent of, say, 60 degrees, 1.7. Tangent of 80 degrees, 5.7. Tangent of 88 degrees, that has a slope of 28. Really, really steep, almost straight up. Tangent of 89.4 degrees, 95. Slope of that line is 95. Really, really straight up, like almost perpendicular. How big can it get? Well, depends on how many 9s you want to type in here. Slope of that line is 57,000. We're buying that it'll get up to infinity, and it will get there right when we're at 90 degrees. What about tangent of 90? Error. That's a, yeah, it'll try to, yeah, I mean, like it'll give me a problem here. It says there's a domain error. Somehow I'm not allowed to put 90 degrees into the tangent function. How come? What's the slope of the straight up line? It's undefined. I mean, like you guys have seen, like a horizontal line has slope of what? 0. Vertical line has slope. It's undefined. That's what we've been calling it undefined for years now. In terms of this y over x business, the point up here is 0, 1. How much is y divided by x up there? It's 1 divided by 0. It's undefined. So Garrett's right. It goes up to infinity, and it gets there at 90 degrees. So what we do is we put a vertical asymptote right there at 90 degrees, and then we draw this guy going up closer and closer.
Is there no way to make the graph calculator?
There is. Did I not do? I thought did we do that real quick one time? Maybe it was in another class. Okay, so very quickly, it's all right. So first, if you were to type in something like this many x's, and then like say subtract 5, do anything? No. Something like that. Graph. It's not vertical, right? I mean, it's got a slope of 99,000. It should have a slope of infinity or undefined. It's close enough to vertical for my purposes. If you really want the calculator to do a vertical line, we should have to type in what kind of a thing. Like x equals 5 would be a vertical line. I can't do it. It's one of the weaknesses of the TI-83, is that you can only do y equals. If you work really hard, and this stuff will make more sense in like a month when we talk about polar coordinates, go back into y equals, it looks completely different. Garrett is yawning, but it looked like a look of surprise, like, oh my God, R1. And then if we do something like, I hope I get this right, 3 divided by cosine, I'm going to hit this button right here. What letter is going to show up? X, not X. Somehow that button doesn't mean X anymore. If I go into the window, again, gobbledygook and stuff that doesn't make a whole lot of sense. And if we graph, we see nothing, of course. 3, I'm pretty sure that should work. Oh, let's go. I did not think about my mode. I tell you guys all the time, think about what mode you're in when you hit the cosine button. So there's a vertical line, a perfectly vertical line. Did you notice how it was drawn? Oh, I'll do it again. Is that how you would draw that vertical line? No, it started at the x-axis, then went up, and then finished up. Somehow it finished. I don't know how it finishes. And then it said, okay, now I'll do the bottom part. So you have to work really hard to get the calculator to do a vertical line. We will talk about some of that stuff in a while. Polar coordinates, right there. Okay, so that's that part. I'm just going to draw the rest of it, and you guys can kind of take my word for it. If you plot more points, you will see something like that. It looks nothing like sine and cosine. It does, however, repeat. What's our fancy word for repeat? Starts with a P. It is periodic. It looks like copies of that thing. Left and right forever. Okay, I think we're up to Kelsey for 11. Okay, so here's what I'm going to do. I'm going to hide the sine. I'm going to hide the cosine. Okay, and what I'm going to do is show tangent. Now it turns out that in this unit circle picture, the length of that green line segment is exactly the value of tangent of the angle that's pictured in here. Now this is new. We haven't mentioned this at all. It's not so important to me, but we'll just mention it real quick, like 30 seconds. First of all, the word tangent. You guys saw the word tangent back in geometry class, didn't you? What's a tangent line for a circle? It's a line that just touches the circle at one point. That green line right there touches the circle at just the one point. It's the same word tangent, and there's a real good reason that it's the same word. So why is the value of the tangent of this angle in here equal to the length of that vertical line? Okay, we know that the tangent is it's the y coordinate over the x coordinate, but not out here. It's the y coordinate over the x coordinate of the unit circle. So let's ignore the y over x stuff because I'm outside the circle. Let's think back to the opposite over adjacent. The opposite side is green. The adjacent side is this dotted thing, not the whole thing, just the, how long is that part from the origin to A? It's 1, it's a unit circle. So when I do opposite over adjacent, green over 1 is really green. So the tangent of that angle is green. It's the length of that line segment. And if I rotate the angle, let's say the angle gets a little bit bigger, what's going to happen to that green line segment if this angle gets a little bigger? It's going to touch in a different spot and it's going to get bigger, isn't it? Like it's just out there at that extension of the line in the circle. So let's see if we can't graph. Whoops. And one other thing, what if my angle is over here, like here? Can you guys see it's the same idea, even down there in the fourth quadrant? Just extend. But now what kind of a number are you going to get for green? A negative. It's down below. Okay, so let's bring this back and we're going to graph. And hopefully we'll see something that looks familiar. There's one piece, it flops around. That's a second piece, and then part of a third piece. We saw the stuff that was in the middle, that's one complete period. Okay, let's come back here. Number 12, Allie. Okay, let's start with the range. The range, remember, is it the x's or the y's? The range is the y's. How low does the tangent graph get? At minus infinity. It gets lower than any number you can name. A lot lower than the -1 that we were seeing for sine and cosine. So the range starts at minus infinity. How high does the tangent graph get? Infinity. So the range is all real numbers. Again, it's really different from sine cosine, which we're trapped between y equals 1 at the top and y equals -1 at the bottom. This guy goes forever both directions. The domain is also different. What's the domain for sine cosine? It's all real numbers, right? You can plug any number you want. You just keep graphing up and down. Is the domain for this tangent thing all real numbers? We're not allowed to put 90 in. Not allowed to put -90 in. Let's think about the next number that we're not allowed to put in. What number is this right here? That's 180. Because how long is a complete period of this, like this purple graph? Isn't it 180? Like 180 degrees to the left and the right. So then this piece in here is only half of that. So it must only be another 90. So 180 is actually okay, but what's the next number, which is a bad one? The 270. Okay, so we got to come up with some way to write. 90 is bad, 180 is okay, 270 is bad, 360 is okay, 450 is like, it's like every other one is okay and every other one is bad. All right, so the domain, maybe we can write it like this. Domain, all real numbers, we're doing theta, so let's do theta. Theta is not equal to, okay, so 90 is a bad one. How far do you have to go to the right to get to the next bad one? There's 180 to the right. So 90 is bad, 90 plus 180 is bad. Suppose you're sitting here at this 270. How far do you have to go to the right to get to the next bad one? There's another 180. You buy that, you just keep going 180s and you'll find bad things. So here's how we indicate, go as many 180s as you want. It's a K. So if K is 7, we're saying add 7 180s. And you'll land on the 7th bad one out there to the right. What if K is negative? Same thing. We'll just go 180s to the left. So that right there is the domain. I guess we should specify that K is an integer. All right, so that's the domain in degree mode. Let's go ahead and put up the domain in radian mode as well. Radian theta not equal to what is 90? You can look at your unit circle if you need to. It's pi over 2. Plus, what is 180? Again, you can look at your unit circle. 180 is pi, and then times the same k that we had before. So it's all numbers except for those, all angles except those. What thing? Oh yeah, this is informally written. Yes, you should, in theory, you should have to put stuff, like theta such that theta is not equal to that. Yeah. Okay, let's look at symmetry. Your general choices for symmetry, it's symmetric over the x-axis or the y-axis or the origin. Thinking about the graph of tangent, is it symmetric over the x-axis? Flip it over the x-axis, does it land on itself? No, right? If you take this part, it's right up here, and you flip it over the x-axis, it does not land on the graph that's already there. How about symmetry over the y-axis? Does this part get flipped over and land on something that was there? No. How about symmetry over the origin? It is. This part right here, if you send things through the origin, they will land on points down here. And the same kind of thing way off here, those guys will end up going to, well, it's kind of off the screen, but out here someplace. So the graph of tangent is symmetric with respect to the origin. Okay, the period. How long does it take to get one complete cycle? 180 degrees. So the period is 180 degrees, or if we're in radian land, pi. Is that the same as the period of sine and cosine? It's not. The period of sine and cosine was 2 pi. Sine and cosine take longer to repeat. Tangent gets there twice as quickly. Okay, asymptotes. Vertical asymptotes here. Where did they happen? It was at 90. There's another one at 270. How can we write where they all happen? Is what we saw for the domain. It's the domain. That's where your vertical asymptotes are. And then the midline, some horizontal line where there's like equal amount of stuff above as there is below. Yeah, it feels like if we're going to say something, it should be the x-axis. But on the other hand, we could argue that how much of the graph lives above that line, infinitely much of it, and how much lives below, the same. Okay, so in some sense it is arbitrary. And if you want to say there is no midline, no problem. I do think it's going to be useful to us to think of the x-axis as being a midline. If I, for example, were to say, take the graph of tangent theta and add 5, what's it going to do to the whole graph? Can you show me with your hands? What will it do to that graph? It's going to shift everything up by 5, including, so like the old x-axis is now up there at y equals 5. So I'm going to say the midline is the x-axis. It's okay if you don't like saying that, that's fine. I'm not going to test you on that kind of thing. Amplitude, how far is it stretched from the middle? Infinitely much. Infinity, or maybe you could say there's no amplitude. Either way is okay with me. And we'll go to Bryce for 13.
At right are the graphs of three function sine, cosine, tangent. Let's identify which is which and point out some nice relations. 0.
Okay, first, can you guys with your neighbors label which one is tangent, which one is sine, and which one is cosine? Okay, we agree with my labels. So tangent is easy, right? It looks so different from the other ones. Sine is the one that starts in the middle and goes up. So this guy right here is your sine. Cosine starts at the top on its way down. Okay, so here's some relationships between these graphs. Can you guys tell me, for example, how much is the tangent at pi? What's the y value at that point? 0. Tangent of pi is 0. How much is the cosine of pi?
0.
Cosine is the graph down at the bottom. That's -1. How much is the sine of pi? Is 0. Okay, 2 of them were 0 and 1 of them was -1. Come over here. How much is, let's say better this way. Which two trig functions are 0 at that point right there? Tangent, and the other one is sine. Which two trig functions are 0 at that point? Tangent and sine. I'm starting to see a pattern here. Wherever one of them is equal to 0, the other one is equal to 0. Let's see if we buy that. Remember this one relationship we saw from my shirt? Tangent is sine over cosine. If it happens that this thing is equal to 0, doesn't much matter what's in the bottom. How much is 0 divided by anything? 0. So if the sine is 0, then automatically the tangent is going to be 0. And vice versa. The only way to make a fraction equal to 0 is to make which part 0? The only way to make a fraction equal 0 is if which part of the fraction is if the top is 0. So if you know that tangent is 0, you're forced to make a sine equal to 0. So we can say that, that the x-intercepts of tangent and sine are the same. Okay, but we feel badly that cosine is left out of the mix. So let's look at the x-intercepts of cosine. So there's one right here, and there's one right there. And let's look at what tangent is doing at those points. What can you tell me about the tangent function at pi over 2? It doesn't exist. In fact, what could I draw in at pi over 2 for the tangent graph? I draw an asymptote. In fact, if you look up at the graph, that's what we had. It was at 90 degrees, which is the same as the pi over 2. So when the cosine is 0, the tangent had this vertical asymptote. How come? Well, if you try to plug in 0 in the bottom of your fraction, what happens to the fraction? It's undefined. And undefined things tend to be infinities or minus infinities. Is the same thing happening over here at the other 0 of cosine, at the other x-intercept? What is tangent doing at 3 pi over 2? Again, it's not defined. So I think I can comfortably say that now, that the x-intercepts of cosine correspond to what? Any questions on those relationships? So I'll say, how does this help? It helped me to try to figure out what the graph of tangent looked like. Once you know the general shape, that it's just increasing the whole time and it's got all these vertical asymptotes, really the only thing you could do wrong is maybe instead of putting it where it is, maybe you accidentally put it in between where it is. Does that make sense? And I can never remember when I was in your shoes, where is tangent? Does it asymptote at the pi's or does it asymptote at the pi over 2's? And as soon as somebody pointed this out to me, I said, oh, I know what sine and cosine look like. That's enough. As soon as you know what sine looks like, well, tangent hits the same x-intercepts. Or if you draw cosine, the x-intercepts become the vertical asymptotes of tangent. So that was enough to help me kind of make sure I didn't put it in between where the tangent really is. Okay, we'll go to the next page and Garrett, number 14.
We have defined ratios involving sides of the right triangle.
Okay, one thing I want to update. You guys have what kind of a circle in your diagram? Unit circle. Let us make it a more general circle with some arbitrary radius r. You guys cross off the 1, make it an r. If you're in the unit circle, what letter is the sine of theta? Sine of theta, the x or the y? Sine of theta is supposed to be the y, cosine of theta is supposed to be the x. But if it's not a unit circle, we have to pay for it. You guys remember how we pay for it? Well, some of you pay for it on the quiz. So there should be an r sine of theta sitting there, but what I'd like to do is put that on the bottom there. And we did write down this y over r at some point, but we've focused so much on the unit circle that I think we kind of lost sight that there should be, it should be y over r is the general thing. And that agrees with our SOHCAHTOA. Opposite over hypotenuse, y over r. Cosine should really be x over r. And tangent doesn't care what kind of a circle you're in. What is tangent? Y over x. Let's go to Stephen for 15. Okay, so we've got 3 new functions, 3 new trig functions. We have sine, cosine, tangent up above. I mean, I could play around with these ratios in other orders, right? I've got x, y, and r. Couldn't I flip some of these fractions over? Well, we're going to flip each of these fractions over, and we're going to give them names. The cosecant is the flipped over of the sine function. So cosecant is really what over what? R over y.
How would that be the flip over of the cosine function?
Yeah, well, I'm prepared to deal with this question because yes, the first time people see it, they are not happy with the definition, and I'll give you a good reason, but let's keep filling in for a second. Secant is the flip over of cosine. What is secant? R over x. Cotan is, okay, well, at least we have one that looks good, right? Cotan is the flip of tan. What is it? X over y. All right, the most important thing for today, there they are. Those are the full-on definitions of all 6 trig functions. I showed you only 3 for the first couple of weeks of our study of trig. There are no more. I'm not hiding any. That's the complete list of the trigonometric functions. Okay, so let's talk about why they're not defined the way that we want them to be. Okay, so are we happy or unhappy with that relationship? Okay, we're happy with that one. But we're not so happy with this one because it kind of crisscrosses from what we'd expect. We'd expect cosine to be somehow related to cosecant. Okay, they're not. Not in the way that you want them to be. I'll tell you what the co-business is. This isn't going to matter to us so much, but let's see if we can do this. Can you guys, what can I ask you to do? Go to your unit circle, and I would like to think about angles that are, so we're talking about this co-business. Do you guys remember another geometry word? Complementary? Anybody remember what it means for 2 angles to be complementary to each other? They add up to 90. That's what it means for 2 angles to be complementary. All right, so for example, 30 degrees has what complement? 60. All right, so that's that. And then I'm going to go to, so that's sine and cosine. And then I'm going to look at secant and cosecant. And the last one will be tangent and cotangent. And what I'd like to do is ask different tables to calculate different things here. Cosecant of 60, 30, and 60. Okay, with your unit circle and the definitions of the 6 trig functions that are right there, no calculators, can I ask this table right here to do sine of 30, cosine of 60. In the corner, you guys are at secant of 30. You guys are cosecant of 60. Here in the middle, tangent 30, and in the front, cotangent 60. Every table have their assignment. No calculators, only the unit circle and the definitions that are right up above. Together, this table up here, how much is a sine of 30 degrees? Perfect. Cosine of 60? 1/2. Sine and cosine, when you plug in complementary angles, are the same. In the back, how much is secant of 30? 2 over root 3. What did you guys get for cosecant of 60? We didn't. We're getting it. Let's get it. Okay, let's get it. Secant of 30 degrees. The secant is defined to be the radius divided by the x. Let's go to our unit circle. We're doing secant of 30 degrees. So we find our 30-degree angle, which is this guy here. We're supposed to do secant, which is what over what? R over x. That's our definition of secant. What is the r for my unit circle? It is 1. The x at this particular point right here is √3 over 2. And that 1 over is really a reciprocal thing, right? So this is really 2 over √3. Secant of 30 degrees is 2 over √3. Yes? Okay. Which one? I forget which one had which. Is that what you guys did or is that what they did? Okay, 2 over √3. Did you guys, can we look at cosecant of 60? What's the definition of cosecant? What over what? R over y. It's all there on the page. Let's look at 60 degrees, which is up here. It's a different point. How much is the radius of my unit circle? It is still 1. How much is the y coordinate of this new point? √3 over 2, which is the same as what we had before. Are there questions on using the unit circle to find secant or cosecant? It's just a matter of using the points. We have x's, we have y's. We should also think about r's. All right, so let's come back and we'll get to our big conclusion. And maybe that can satisfy some folks who are unhappy with these definitions here. Secant of 30 and cosecant of 60. What's true about them? They're the same. 30 and 60 are complements. Secant and cosecant have the same value when you plug in the complementary angles. Tangent of 30 here in the middle. What did you guys get? Answer, Kyle? 1/2 of √3 over 2, which is a 1 over √3. Just simplifying it. What did you guys get for cotangent of 60? 1 over √3. What's the relationship? Equal. This is why we use the co in a way that is not what you wanted for this reciprocal stuff. It's just a different choice that was made. So the co has to do with not the reciprocals, but rather with the complementary angles. We're not going to use that complementary business very much, but anyway, that's why the definitions don't match up with what we were hoping for. Okay, let's go to 16. Is it Stephen? No, Stephen, you went. Garrett? Okay, so which one did we say? Secant? All right, so let me show you a secant. I'll erase that. Okay, it turns out that the secant of this angle right here is the length of that turquoise line. That turquoise line is not a line we've looked at before, although kind of did, because we looked at the green tangent one before. The turquoise is just the hypotenuse of that bigger triangle. It's not the radius of the circle. It goes outside the circle. But for some reason, and you can kind of think about the geometry a little bit, the secant of the angle is the length of that extended hypotenuse. And if we graph, and we plot a bunch of points, then we will see the graph of secant of theta. We will see part of the graph of secant of theta. So I don't know if I can draw on this. Can I draw on this? It does not appear that I can draw on this. Well, I think that, I mean, I can certainly scroll up, but there should be a picture down at the bottom, and I don't know why there isn't one. So let's show you on your graphing calculator. Is there a button that says secant on the calculator? There is not. Even if you go into the catalog, you will not find a word that says secant. The calculator does not know what secant is. So what we need to do is use our brain is a 1 divided by. So let's come here. The definition of secant is r divided by x. Said another way, secant is the reciprocal of which one? Secant goes with cosine. Secant is 1 divided by cosine. If I type into my calculator here, 1 divided by cosine, I will find the graph for secant. So that looks okay, that looks okay, it's probably good. Okay, there's the graph of secant of theta. Those vertical lines are not part of the graph. That's the calculator's best effort. It's vertical asymptotes that it's drawing. So the secant just has a bunch of these cups, upside down, right side up, upside down, right side up, forever both ways. Okay? It's very tempting to hit that button right there. I typed in 1 divided by cosine, and there is a button right here in yellow. It says cosine to the -1, and that -1 power in many instances represents 1 over, not here. So this cosine to the -1 is what we will spend the next 3 days talking about.
You already gave us the homework problem.
Did I?
Yeah, I spent like 30 minutes trying to do it.
Oh, that's right. I should not have given that homework problem. My bad. Okay, 17, we're going to skip over. Well, I'll just write down one thing. Turns out there's lots of nice relationships that are true for these different trig functions. We've seen some of them up above with this 1 over business. If you take a look at something following the learning objectives, you'll see a reference sheet, and you'll see some stuff that we've written. We've got our, I guess I should change these to R's instead of 1s. That would be better. But we've got our 6 trig functions right there. We've got some SOHCAHTOA stuff happening over here. We've got this tangent is sine over cosine. We've seen that. We just looked at which one? This one right here, that secant is 1 over cosine, the reciprocal. It turns out there are these nifty things called the Pythagorean identities. For example, sine squared of theta plus cosine squared of theta is equal to 1, no matter what angle you plug in for theta. First, we got to make sure that we understand what this sine squared means. It's what's happening right here. If you see cosine squared, it means you take the cosine of theta, you find that number, and then you square it. You don't square the angle theta. We will hardly ever have reason to square an angle, but you take the whole angle, you find its value of cosine, then you square it. So as a quick example on the calculator here, if I were to come out here and say, type in, I'm looking for this equation, sine squared plus cosine squared. If I type in sine of 32, let's go to degrees. If I type in sine of 32 degrees and I square it, that's squaring the whole, not 32 degrees, not squaring 32. It's finding sine of 32 and squaring it. And if I add what? Cosine of 32, and I square that, sine of 32, is it a nice number? There's hardly any nice numbers on that unit circle. Sine of 32 is not a nice number. If you square it, it's still not a nice number. Cosine of 32 is likewise not a nice number. Square it, it's still not nice. Add up these two not nice numbers, you get 1. I'll show you. Sine of 32. Not nice. Squared. Equally not nice. Same thing is true for cosine. Cosine of 32, if you square it, you get some not nice number. But look at what happens when you add those two not nice numbers. You see it? We get a very nice number. Everything matches perfectly. This would be a great example. So my son is like 8 or 9 months old. So I'm going to teach him adding with carrying, and this will be the first example that I give him. Right? Everything works left to right. You know, 9 carry the, like 0 carry the 1, 0 carry the 1, 0 carry the 1, eventually 1. Okay, so the last thing I want to do here, and then you guys will have a few minutes to do some group stuff. It's 18. Go to Hillary.
Found the value of one of the trig functions at some angle. We can use our identities to find the value of the other 5 trig functions. For example, suppose theta, fourth quadrant, cosine theta, equals
Okay, I'm just going to do it in one way, and that's the way that I prefer. If you prefer a different way, that's fine. So here's the idea. You have some angle in the fourth quadrant, so I'm just going to draw some random angle in the fourth quadrant. So theta goes all the way around there. And I know that the cosine of that angle is 12 over 13. First of all, does it make sense that the cosine is positive down there? Does that agree with stuff we've seen before? Remember the all students take calculus thing? Well, you might remember the other one, but this is the one we'll say on tape. So what trig function is positive down here? Cosine, only cosine. Okay, now we can know the full truth. Which is the reciprocal of cosine? Which function? Secant. Secant is the one that's related to cosine. It's not what we hoped. So actually saying only cosine is positive down here is a lie. What else is positive down here? Secant is positive down here. Okay, so cosine is 12 over 13. I'm going to go ahead and draw a right triangle here because I can think of this point right here as being the one that's on the circle. In terms of x's, y's, and r's, what is cosine? Use x's, y's, and r's. What is cosine? It's x over r. Again, most important thing is that list of 6 things that we defined up above. Okay, so then how much is x in this example? It's 12. So the point right here is 12, comma. How much is r in this example? 13. So I'll put a 13 on my radius. And I don't know the y, but could I find the y? Let's see, so the x we said was 12, so that's a 12 there. And then how would we find the y? Is it 13 over 12? Yeah, have a right triangle. One leg is 12, hypotenuse is 13. Use the Pythagorean theorem. We can find that other side. We know that a squared plus b squared is c squared. 12 squared plus y squared is 13 squared. How much is y? It's the square root of 25, which is how much? 5. Are there any other numbers that solve that previous equation? Yeah, isn't there a plus or minus here? Right. Y squared equals 25 has 2 different answers. You have to pick the right one. Look at the point. Is the y coordinate there 5 or is the y coordinate there -5? It's -5. You have to think about the geometry. The fact that this is in the 4th quadrant dictates which one you pick. Don't pick +5. It's not. And I know that that some of you guys have lost points like in algebra classes because you forgot that when you have a y squared equals, there's a plus or minus in your answer. You're going to lose points again for the same reason if you don't forget that plus or minus here. I don't really care about the algebra part. I don't care that there's a plus or minus that you're supposed to remember to put in. I do care that if you put +5, you're going to get all the wrong answers. It's not +5. The y coordinate is -5. Garrett?
How would you do that if it wasn't actually polar? That's that it was like an ugly
Oh, I see. So like if I said cosine of theta was 0.864, I don't know what that number is, over 2, something like that. Yeah, so then make it over 1 and yeah, good question.
But that means the radius.
The radius is 1,
yeah.
And the x coordinate is 0.8642.
Wouldn't it be possible if the radius was actually something larger than that? The constant is also larger and it's
It's true. And it's true here for the 12 and 13. You guys agree? I made an assumption. I said, oh, so if x is the thing on top, then x is 12. But isn't it possible that x and r were much bigger and they just reduced to 12 and 13? It's true. And so maybe this 5 isn't really a 5, it's some bigger number. But when we do all our ratios with sine, cosine, and tangent, they will all reduce down. So no matter what version of 12 over 13 you write, we're going to get the same answer at the end for sine and for cosine and tangent. The ratios will all be good as long as we're, yeah. Okay, so then as soon as you have your x and your y and your r, you know everything. And I'm just going to write down one of the 6 trig functions, and you could write all of them. I will do cosecant. Again, look back at the top. Cosecant in terms of x, y, and r. What is cosecant? Cosecant is y. No, it's not. You guys are lying to me. Cosecant is r over y. How much is the r in this picture? 13. The r is always going to be a positive. The x and y could be negative. How much is the y? -5. The answer here is -13/5. That's cosecant of this angle. Questions on that? Okay, so in the time we have left, about eight minutes or so, you guys are going to do a bunch of examples just like this. I think this is an important thing to kind of gain comfort with these new trig functions. Keep going back to the x, y, and r stuff and draw a picture for every example on the next page.